Alright, to find the outer loop, the process will be nearly identical, meaning that we will start off with slicing up the entire region with tiny little sectors. We agreed that the area for such a sector would be the r squared over 2 times the differential angle, where that's the differential angle right there. We will add them all up using the grace and elegance of the fundamental theorem of calculus. That would give us that the sum of all the little areas would be the sum of 3 plus 7 cosine theta squared over 2 times d theta. Easy enough. And of course I want theta limits. Now here it's important to figure out when is the outer loop being traced. By plugging in values you could just make a small little hold on. So by tracing, you can make a little chart and follow the line as it's being traced throughout various angles. So for example, theta r, when theta is equal to 0, r is equal to 10, so you know you're right here when theta is equal to 0. When theta is equal to 30 degrees, 60 degrees for example, 60 degrees, cosine is 1/2, so that's 3.5, you know that's 6.5. So at 60 degrees is 6.5, 1, 2, 3, 4, 5, 6, 6.5, I told you. And so on and so forth. We calculated this angle before by setting r is equal to 0. R is equal to 0 gives you the points where the graph crosses the origin. We computed that in the previous slide. I think it was something like this. We had computed it here. No, not there. There. We had computed it before when the radius was 2.0. Here r is equal to 2.0 approximately. That's when you get to that point. So you want to stop right there. If you keep going you'll start tracing the inner loop. We just wanted to trace the outer loop, so I'll just go with half of it and then I'll multiply by 2. So forget about the bottom for now. We'll just go from 0 to 2.0, and this will give us the area of the top part of the outer loop. Okay, so to do that to do that is not so bad. All right, we did it before. This was 1/2 times the integral of 3 squared, which would be 9, and 21. I think I did that incorrectly last time. That's 21 times 2. That would be 42 times cosine theta plus 49 times cosine squared theta, and all this times d theta, and all that going from 0 to 2.0 radians. And then the rest of that is quite easy. You should use an identity here. I'll take it one step further. 0 to 2.0, 9 plus 42 times cosine theta plus 49 times 1/2 plus 49 over 2 times 1/2 times cosine of double the angle. And now this is really very doable. The integral of that is quite basic. And then you evaluate it from 0 to 2 pi, and that of course would give you the area of the outer loop. Okay, and just to be completely correct here, you should note that I made a mistake. This one right here should have been 21 times 2. That would have been 42. 42. Alright, that's it. Incidentally, so suppose that we just found out the area on the outer loop, and in the prior example we found out the area inside the loop. Now what if you wanted to find the area in between? Well, you just subtract the 2, and of course that would give you the area on the in between the loops. Here don't forget to on the outer one, where's the outer one? Yeah, there. Don't forget that what we did here from 0 to 2, we're just calculating the outer loop. So when you're done with this, you have to double the area so that you get both the top and the bottom. Okay. Alright, we'll stop there for the outer loop. We'll come back and do more areas on polar coordinates.